Okay, so let's look at this question together. It says a person pulls on a rope with a force of 100 newtons. The rope makes an angle of 50 degrees with the horizontal. It's attached to a 25 kilogram sled. The sled experiences a constant friction force of 10 newtons. Calculate the acceleration of the sled. So this is clearly a problem that involves acceleration and forces. We're going to have to use net force equals mass times acceleration to solve this. But it's a complicated problem. It's got a variety of different forces pointing at an angle. So what we always do, what a physicist would do first in a situation like this, is draw a really accurate diagram of all of the forces that are acting on the object. So let's do that. We did this in class. We're going to do a simpler version of it here. So first off, I'm going to draw a dot that represents the sled. The reason I'm drawing the sled is because the sled is the object that's accelerating. We don't really care about the person. We care about the acceleration of the sled, so we want to draw the forces that are acting on the sled. What I always recommend is draw gravity first. If you're on the Earth, there's going to be a force of gravity. Now I'm going to label this Fg. I know in class we were doing subscripts, like the force on the sled by the Earth. That was to really understand Newton's third law, and I think we have that down now. So it's much simpler if we just label it with simple subscripts. So that one's going to be labeled Fg. And then I mentioned to you, you should just think about what's touching the object. Anything that's touching it is going to exert a force on it. So the ground is touching the sled. One force that the ground will exert on the sled is a repulsive force, an upward force that's going to look like this. And that's called normal force. Whenever an object touches a surface, the surface always repels it straight away from itself with a force that we call the normal force. That's the electrons repelling one another. And again, a simple label here. I'm not going to worry about force on the sled by the ground. And I'm not drawing the action-reaction pairs either. This is a simple diagram. It's called a free body diagram because it's free of its surroundings, free of all those extra cluttering things. All right, so the ground is touching the sled. The ground exerts a normal force. Something that you have to be careful about is things like the ground or the floor not only exert normal forces, but they might exert friction forces. And this problem clearly indicates that there is a friction force. In fact, they tell us the value of it. It's 10 newtons. So I'm going to label that 10 Newton backward friction force. So those are the two forces that the ground exerts. What else touches the sled? Well, there's a rope touching the sled. And so now we want to draw in the force that the person is exerting on the rope. Technically, it's a tension force. You always draw tension forces pointing in the direction that the rope is pointing. So that's at a 50-degree angle. And here, it might be convenient to draw a dotted line to represent the x and the y axes. And that's really why we represent objects as dots. There's supposed to be a dot at the origin of the coordinate system. So now if I draw a line that's at a 50-degree angle to the x-axis, and I can label that 100 newtons. That represents the force that the person is exerting on the rope. Is there anything else touching the object? No, there isn't. So that's it. Those are the four forces that are acting on the object. And our job is to find acceleration. So as I said, we're going to use net force equals mass times acceleration. However, we have the issue that this force is pointing at an angle. So it's partially pulling forward. In fact, I can draw that component. So this much of the force is pulling forward, but it's also partially pulling upward. So it's acting partially in the x direction and partially in the y direction. And this is a lot like the projectile motion problems that we solved in the past, where something has a launch velocity at an angle. So part of that velocity is forward and part of that velocity is upward. And just like in those problems, we had to figure out and calculate the x and the y components. We're going to have to do that too here with forces. But it's done the same way. Since the x component is adjacent to the hypotenuse, we can use cosine for that. So this is going to be 100 times the cosine of 50. And since the y component is opposite the 50-degree angle, we can use sine, 100 times the sine of 50. And I got a calculator here. I'm going to quickly calculate those values. And it turns out that this is equal to 64.3 newtons approximately. And when I use the sine to do that, it's equal to 76.6 newtons. So that's an important step. you can never mix x and y things together, whether they're velocities or forces. You can't mix them together. And anything that's at an angle, partially in both x and y, you always have to figure out the x components and the y components so that you can treat them separately. And I should mention to you that in some problems, you might not know the value of the hypotenuse. Let me show you this over here on the side. So I could have said that we don't know how much force the person is pulling with, but it's still at a 50-degree angle, in which case you can still say that the x component is f cosine 50, and the y component is f sine 50, and then you can proceed from there. So sometimes you may not know the hypotenuse, in which case you sort of have to leave the algebra symbol in your results, and later on you'll figure out what that is. But that's not in this case. So let's go back to this particular problem right here. Now we're ready to use our formula, net force equals mass times acceleration. But as I said, just like in a projectile motion problem, you have to do the x and the y direction separately. So let's add up the forces in the x direction. That'll give us the acceleration in the x direction. I chose x first because it's pretty clear from the description of this problem that the sled is going to be moving in the horizontal direction, not in the vertical direction. So now I'm going to literally follow the directions that this symbol is saying. This symbol is telling me add up the forces that are in the x direction. This is why we draw these diagrams so carefully. Because now all you have to do is look at your diagram and literally write down the forces you see in this diagram in the x direction. So here's one right here, 10 newtons. Now it points to the left, so that's negative 10. The only other force in the x direction is this one right here, 64.3, and it points to the right, so it's positive 64.3. And that's it. I've just followed those directions. I've added up the forces in the x direction. That equals the mass, which was given in the problem as 25, times the acceleration in the x direction. And now it's just a simple algebra problem. 64.3 minus 10 is 54.3, and I'm going to divide that by 25, and I'm going to get the answer to our question, which is 2.172 meters per second squared. And that's it. That's how you do a problem like that. Now, you may also get another question, and let's try this one as well, and that is, how about this normal force? What does the normal force equal? And if you're watching this on video, you might want to just pause the video right now and see if you can figure out the answer to that question on your own. So pause the video, see if you can calculate what the normal force is equal to. Okay, if you're back, hopefully you got the right answer. Let's see how we should do this. So what you want to do, the normal force is in the y direction, so let's add up all the forces in the y direction, and that equals mass times acceleration in the y direction. So again, this is telling us, look at your diagram, add up all the forces in the y direction. All right, so one of them is the normal force, and that points up, so it's positive Fn. I see also, well, not the 100, but the 76.6. That also points upward. And so maybe some people think that the 76.6 and the normal force are the same thing, but they're not. They're totally different. The 76.6 is just the vertical component of this 100 Newton tension force. It has nothing to do with the normal force. They're two different forces. It's okay to have two different forces pointing in the same direction. They're both positive. Also in the y direction is Fg. Now that points down, so it's negative. And that's it. Those are the only three forces in the y direction. The mass is still 25. How about the acceleration in the y direction? I mean, if we don't know it, we have a lot of unknowns here. Well, it turns out that we do know it. I think we can assume by looking at the situation here that this sled is only moving in the x direction. There's nothing in this problem that indicates that it's coming up off the ground, which means the acceleration in the y direction is 0. And you know, this is pretty much an assumption that you can always make, is that you're going to have acceleration in one direction, either the x or the y, but you will not have acceleration in the other direction. In fact, in the future, we'll learn how to set up problems so that you always have 0 acceleration in one of your directions. And that makes the problem easier to solve. So let's continue here. We still have two unknowns. We're looking for Fn, but I don't have anything in here for Fg. So the other thing that's very common is that you're going to be using your formula for Fg. If you look at your formula card, or if you remember, Fg equals m times g. So let's do that in math. So the M is 25, G is 9.8. And really be careful about this. I've said many times in class that the symbol G represents 9.8, not negative 9.8. It represents 9.8. And here you can see why it's important that you don't put a negative here. We already have a negative over here. By looking at our picture, we've already said that the force of gravity points downward. If we also put a negative here, we're going to have a double negative, and essentially we're going to create a positive force, which is wrong. So G represents 9.8, not negative 9.8. This side of the equation is 0, and so we can get our answer. The normal force is equal to, well, 25 times 9.8 is 245, and then we're going to subtract 76.6 from that. So the final answer here is 168.4 newtons. What's happening here is the fact that the person is pulling slightly upward on the rope. That means that the floor doesn't have to support the box as much. And so the normal force is 168.4 newtons, which is less than the weight. The weight is 25 times 9.8, or 245 newtons. So hopefully that'll get you started on how to do problems where forces are at angles in two different dimensions.